Thanks, Giannis. I'm actually grateful to come right after that discussion from Alan and Naucheng because this project perfectly represents that you need high time cadence observations and polarization to sort of go along with what we've been talking about. And Alan presented an overview of sort of the last 10 years of BLAC, whereas this is specifically going to be in terms of about a week of time in September of 2019. And the main motivator for this project was actually the TESS spacecraft. And that's the satellite that's shown down here in the bottom right. And here we go. TESS is the Transiting Exoplanet Survey Satellite. And so I'm just going to spend a brief amount of time going over it because not everybody here may be familiar with it because it doesn't do polarization. It's purely a photometry mission, but it's to monitor 500,000 nearby planets or nearby stars, exoplanets, in an area of sky much larger than Kepler. It observes a particular sector of the sky for about a month. And it's actually 4 wide field of view cameras that are all aligned to get that whole sector. But the main thing is that we can get really high cadence photometry observations going down to 2 minutes, or even now, as we're going into the extended mission, they've driven that down to about 20 seconds, 20-second cadence observation for the entire month for particular objects that TESS might be looking in that particular direction of the sky. So we actually looked ahead back in 2019 and saw that BLAC was coming up. And so we decided to concentrate and do a high cadence time resolution observation multi-wavelength campaign of BLAC during this month to coincide with these TESS observations. So we asked for and got 2-minute cadence observations for the whole month. So that's about 16,000 data points of photometry for BLAC with TESS. And then we went ahead and got gamma rays with Fermi. We got about a week of time with NuSTAR and SWIFT, as well as SWIFT gave us more UV coverage. And then we went to our collaborators at the Whole Earth Laser Telescope collaboration and got optical wavebands and specifically polarization for this conference. And I just want to highlight, because I couldn't put everybody's names on here, I just wanted to quickly mention that all of our collaborators were distributed around the world so we could get near uniform coverage from the ground as well as we could from space with TESS. So this is the month of observations, first in gamma ray at the top here, and then the optical in the middle. And TESS is also an optical band more towards the RNI band than anything else. And so we have over the entire month of time in September of 2019. We see actually really good correlation between the optical ground-based variations and the TESS variations, which is good because there's a few nitpicky things with TESS that are kind of an issue. But luckily we don't see those showing up in the data because it correlates well with the optical. But this red panel highlighted section is this week of overlapping time that we had with NuSTAR and SWIFT. So I'm going to focus very much in on that. I'm going to briefly show all of our data before quickly just going straight into the polarization, because that's the main focus of this conference. So here is all of our data for that week. We have the gamma rays up here in the top left with the upper limits going down through the hard and soft X-rays. And then we have the UV data down here in the bottom left. If you jump up to the top right, then there's the optical data in the BV and R bands. Then we have the 2 polarization, the degree and position angle, the I band, and then finally the TESS light curve down here. These 2 black vertical lines are actually showing the 2 peaks that we see in the data during this week of time. We have a very strong optical peak here later in the week, and we have a decently strong higher energy peak here earlier in the week that isn't quite as well seen in the optical, but we were still able to pick up. And we were actually very lucky that we got this very nice rise and then decay in the optical that we saw everywhere, that if we had observed for a couple more hours with SWIFT and NuSTAR, we would have gotten, but we were unlucky in that regard. I just quickly want to go over we did a brief correlation analysis. We did it based off the test data because it's so finely sampled that we were able to drive our errors really, really far down and have very low uncertainties. And so we see that TESS on the optical, there's a perfect correlation there. Gamma ray, it overlaps amongst the uncertainties of the gamma ray time bending. But we see that the X-rays, there's actually a lag, and that the optical data variability leads the X-ray variability by up to about 0.4 days. And so if we look at that sort of based in frequency space, we were able to go and get a shock model and fit a magnetic field strength of about 3 Gauss to these time lag variations and conclude that the shock model works well for this correlation that we're seeing. So moving right into the polarization behavior, we had polarization data from about 5 main observatories. We had to just check some stuff real quick before we're able to determine anything. There's a molecular cloud that lies along the line of sight to BLAC. That's more of an issue in the X-ray data than it is with our stuff. But we wanted to check for the comparison stars that are along that main line of sight. We went to Gaia and obtained the distances to the main comparison stars, found that all the stars lie beyond the cloud, so there's normal reduction methods. We can account for the cloud absorption and polarization there. The average cloud parameters are really, really low compared to the BLAC polarization, so we don't have any issues. We also corrected all the data for the host galaxy contamination. So here's our polarization curves over time for just that week period. And we see moderately strong polarization between anywhere from 4 to 10% during this week. And as Alan was saying, that if you actually look at very high finely sampled polarization, we see with this dotted line, this is the position angle of the jet. So all the polarization along this line is parallel to the jet. And so we can see that over time, for the most part, we are parallel to the average jet direction, at least the radio jet direction. But we do see upwards of 40, 45 degree angle swings away from parallel before, at least in this case, going back. There's also a lot of variability that we can see, especially in the degree of polarization. If we focus on this peak here, which was when we had that nice well-defined optical peak, we see a polarization that increased and then decreased and is doing some crazy stuff overnight. And this is the type of thing that you wouldn't see if you were only to observe a source once or twice a night in polarization. You have to hit it many, many times in order to make out this sort of variability. And we figured out the minimum time for polarization doubling, and that was about 5 hours. Looking in the QU plane, there's actually some notable structure. If we start off early in the week, we have QU SOAK parameters around here, and then there's these sort of rotations in the QU plane over the course of the week, down here to very low Q values and then up to high again, as we sort of rotate around in the QU plane. This structure you wouldn't have been able to see just looking at the degree and positioning of the polarization, but they're very evident in the QU plane. But these variations are not necessarily linearly related to the brightness. So that's what this is showing on the right, just the values of the Q and U Stokes parameters and the optical brightness. And so actually this nonlinear Q and U brightness with time suggests that there's multiple emission components, which we interpreted in this project as evidence for turbulence. We calculated there's about 130 turbulent cells at this particular period of time. The observed standard deviation for the degree of polarization was about 2.1%, whereas our expected under the turbulence model, we expected about 3.4. What this means is that we require at least a partially ordered magnetic field structure. For example, this could come from a shock compressed turbulent plasma or turbulence in a helical magnetic field. We didn't really venture into sort of the implications of that, but this is just sort of what we're seeing in this 5 days of time with BLAC.
2 more minutes.
Thanks. Since I have just about 2 minutes, I'm just going to highlight our additional observational results. The source BLAC was optically variable for about 20% of the time. We statistically figured that out with a one-way analysis variance test with a minimum timescale of variability of about 30 minutes. The average timescale was about 15 hours, which matches well. We did the same thing for the X-ray timescale of variability, which had a minimum timescale of about 15 hours as well. So there might be some correlation there that we haven't quite fully figured out yet, just because we've only been looking for about 5 days. There is that noted bluer when brighter trend with this source, as there are in other sources. The change in the spectral shape can't be explained purely by a change in Doppler factor, and the accretion disk doesn't help explain that spectral variability as well. So there's other stuff going on that would cause this variability. So I'll just throw up my conclusions really quick. The high time resolution multiwavelength data can reveal a tremendous amount. We just need a lot of time on telescopes, or especially dedicated telescopes like TESS, to figure that out. TESS beats what we can do from the ground, but it only looks at a particular source for a month and then turns away and won't go back to it for about 2 years. So there's a lot of downtime that ground-based telescopes can make up for that. In the case of BLAC for this week, it was likely caused by a turbulent plasma passing through a shock and decaying in energy. This needs to be applied to more blazars, though. A lot more blazars are observed with TESS because it's looking at the entire sky. And these, it'd be great if we could get high cadence, high temporal resolution polarization observations of these sources at the same time as TESS is looking at it. There's several instances. So this is 2155 minus 304. This is the preliminary TESS light curve. And then our collaborators have done some stuff with S50716, as well as S40954 with the TESS light curves that show examples of what we can do with tests, but would be great to have polarization for in the future. And with that, I will happily take any questions if there are any.
Thank you very much, Zach. I see Antonio has his hand raised. Antonio, go ahead.
Yes, thanks. Zachary, thanks for your talk. Great talk. I was just curious whether you were able to estimate the energy in the random component of the magnetic field versus the regular component. Thanks.
We didn't look into that. We did, like I said, in our shock model, we got a magnetic field strength of about 3 Gauss in the jet, but we didn't explicitly try to resolve in between to the ordered versus turbulent chaotic part of the magnetic field.
Okay, thanks.